I'm doing computer engineering, which basically means you do electrical engineering, means you go as much as you can into the direction of computer science. I got my Bachelor of Science in October last year, and I'm currently involved in the master's program. So otherwise, when I'm not talking about C or studying or whatever, you might sort of find me in the XMPP community. And well, where I work on a Euro XMPP server called Prosody, and in that context wrote some C bindings, so Euro to C bindings. And I'm working with some other people on an Objective-C XMPP library, which noteworthy is not based on Cocoa, so it's actually portable. Also being in the electrical engineering student, and obviously all the programming work you sort of get to do is quite close to hardware, so it involves a lot of getting to know C. So that's basically my motivation for doing this talk. Okay, so what are we talking about? So the disclaimer, what are we talking about? We're not talking about. I'm going to talk about C99, so it's a revision as a standard which was published in 1999. And everything I will talk about will also apply to C2011. Published in December last year. What we're not going to talk about is C++. That's a separate standard, different rules applying, apparently completely different rules in some cases. I'm not fully aware of them because I don't do a lot of C++. We are going to talk about Objective-C in some sense because while we're not going to cover any objective aspects of Objective-C, it is a real superset. So everything that applies to C99, if you compile Objective-C into C99 mode, will apply there. Okay, so quick overview. We're going to start out talking about undefined behavior, what that is exactly. Then we're going to talk about the strict aliasing rule, which some of you might know, a lot of you might not know. It's actually a special case of undefined behavior, but it's noteworthy to make it separate. Then we're going to talk about arrays, and you're all thinking, why are we talking about arrays? It's completely boring. I hope it's not going to be. We're going to talk specifically about multidimensional arrays because I get the feeling that some people are confused about them in some cases. Then we're talking about different conversion rules in C, which also some people tend to confuse, and they're actually somewhat hard if you want to get all of them in your head. That'll be what happens when I add two numbers of completely different types and what's cast to what and all those things. And then we're going to, well, have some fun with C99. So basically, what you see in C99 that's actually fun and interesting to use above ANSI C. Okay, so undefined behavior. Well, what is that? The C standard defines multiple types of behavior. This is implementation-defined behavior, which is implementation-defined, so each compiler makes its own choice. And it says 70% should be documented. So your compiler does something, puts in the documentation what is the exact behavior we are doing, and that happens. There's unspecified behavior, where the C standard guarantees you that one thing out of that of things will happen. And then there's undefined behavior. And undefined behavior is what we're going to talk about here. And basically means there are no rules enforced by the standard for this specific case. Which means anything may happen. The evil example that no compiler will actually implement, obviously, is well, he might format your C drive because you invoke undefined behavior. Any program that contains such behavior is erroneous. And we're going to see some examples of what you need to do to invoke undefined behavior and when your compiler may format your C drive or not. Basically, the thing is you can do anything from issuing a warning, issuing an error, or just compile a program and something strange happens at runtime. So, as a sort of motivation, as a breakdown of intuition, I have this who wants to be a millionaire type of questions for you, just to see whether you actually know what you think you're doing. So, let's say we have this snippet of C code, right? And the question is, what does it usually print if you don't optimize it and you're in x86? So let me talk about a bit about this snippet. We have an unanswered integer with 32-bit width, and it's assigned a 1. Then it's, well, shifted by 32-bit, and then we print it. And that's actually something apparently people don't know, and it's interesting to me they don't. The C standard nicely defines for us ways to print this fixed with integer types. Basically, what this macro is, it's just a define for another string, and then you string concatenations. So you don't have to guess, is it %I or is it %li, you just use this macro and you're fine. So, okay, what would any of you think? You think this prints a 0. Okay, so who would think this prints a 1? I'd say that's less. Who thinks this prints a 42? Okay, and neither? Okay, so the correct, in some way, answer in this case is 1. So, just to guess the clue, because who has an idea why this prints 1 without saying what it is, but who has an idea why this might be 1? Please raise your hand.
Yeah, you may only shift by 31. 32 is 1.
Okay, so, well, I'm going to give you you may only shift with 31, that's correct. The thing is why this has happened and why did they actually do it like this. It's interesting because this is different among platforms. If you're using a 32-bit x86 system and even 64-bit x86 system, for 32-bit types, so if you map to assembler for 32-bit registers, the shift basically has a certain space it allocates for the shift demand, and that's 5 bits. And 5 bits can contain numbers up to 31. So you specify 32, you encode it as an integer, cut off the last 5 bits, use that, and that's all zeros. So you shift the 1 by an amount of 0. If you do the same thing on a power PC, the results are actually 0, because they have 6 bits for the same purpose. So the 1 is included, and you get zeros. So this is the typical case for why they put undefined behavior in the C stack. Because, of course, you can special case sort of thing like, okay, if the user has something more than 32, then you just set it to 0 hard with a mod instead of a left shift left, logical shift left. But that's just unperforming, and you don't really want that. So the rules, so this is quoted for the left shift left operand. If the value of the right operand, so that's the shift command, is negative or is greater than or equal to the width of the promoted left operand's behavior is undefined. So that's what happens there. It's 1 even though you probably expect 0, and it might be 0 on a different platform. And if you're on a 64-bit systems, maybe he didn't use enough space to actually be able to shift up to 64. Maybe he didn't. If you optimize it on a 64-bit system, it's actually 0 because then he uses RAX instead of EAX. With all those different, interesting kind of behaviors you can get out there if you just compile it differently. So they use it. I mean, in the end, it's the same thing as setting it to 0 if you were doing it on purpose, and you probably just weren't doing it on purpose anyway. So, different question. This is about integers overflowing. So someone worked this, in his opinion, very clever code to check, okay, I want to allocate a buffer for a string, and the string is n characters long, so I need a byte for the 0 character. So I allocate n plus 1, and now I need to check somehow, does that overflow if I add the 1 to the size the user gave me. So presume we have this code, and we have this check where he aborts if it overflows. So the assumption here is if the sign integer overflows, it becomes negative, we abort. And let's say the size is actually int max, so adding 1 makes it overflow. So what would you think this code prints? Who thinks this prints nothing at all? Okay. Who thinks this prints aborted? Few. Who thinks this prints fetch in memory? Okay. And who thinks this prints size? Okay. So I mean, I sort of gave it away, and in a way, of course, a lot of this question's answers are obviously not what you expect them to be. There are some coming up, fortunately, where they are what you'd expect them to be, so still have you guessing. Indeed, it prints fetch in memory in this case, which is the meritative set. And the reason is just that if you optimize this code, what happens is, okay, so size plus 1 is obviously larger than size because it's size but incremented by 1. So this whole if statement is optimized away. It just never happens.
Yep.
twice. So we invoke undefined behavior. If we had an unsigned integer type, overflow is actually well defined. If you have the maximum value for an unsigned integer type, you add 1, it's always 0. That's well defined. If you have a signed integer, not so much, because the overflow is just undefined, that what's happening there. And yeah, reverse aside, if max plus 1 is just not in min, it doesn't wrap around to the negative value, which was the assumption in the previous slide. And I mean, obviously the real solution in this case is, okay, check it against int max. If it's int max, you can't just add 1 or cast it to something larger than the type you got as an argument. I think that will work just fine. Okay, yeah. So this is what I said before again. But I want to talk about this thing. So the thing is, you can think of this, and this is in a lot of cases useful to think of it as case collapse. So you have multiple cases. Here's the case, and either your behavior is defined, and then size plus 1 can never overflow, and size plus 1 is obviously larger than size. Or you have the case your behavior is undefined, size plus 1 is something, and well, something could be larger than size, and behavior is undefined anyway, so your case collapses to being false too, because undefined or false might as well be false. And if you're an optimizing compiler, you're just going to do that. So this is if false, and the old statements go away. Okay, then there's some undefined behavior you operate in U. You might not have known that's the name for it. Obviously, you're referencing a null pointer. You're referencing a wild pointer, which is basically take a number, pass it to a pointer dereference it, so memory just doesn't belong to you. Read memory or anything like that. And then two high array instances, which basically is, if you think about what that does, a wild pointer, because it just reads past the array and you see. But okay, so then some mitigation. So we want to avoid it, right? There's some different things you can do. You can use compiler warnings, and obviously just specifying W all helps, and of course we all do that because we like our warnings and we read them all and we correct them all. And use W errors so we don't miss any of them, right? So then, if that doesn't help, or if your compiler doesn't want, there's something you can do in Clang, which is interesting. You have flags called fcatch undefined behavior and ftrap v. And what they do is effectively they generate code that's executed at runtime and checks your variables. Right? The shift amount might not be the constant. We can easily check this might be a variable, which is derived from some user input, so you need to check this at runtime. So this introduces runtime checks, which actually just check, okay, is this larger than 31? If it is larger than 31, it executes a trap, which basically means your program will crash. So it's not ideal. It's, if you have it in a network application, definitely a DOS. But if you use it during debugging, you have a nice advantage, because if your compiler generated code that just worked for your platform, but in fact was undefined behavior, it will suddenly not just work for your platform, but it will crash. You will have a reason to debug this. Similar thing for ftrap v. This is just the same thing, but specifically for signed integer overflow. Introduces this checks basically against int max. Then if you really want to, you can make signed integer overflow wrap. So this is the minus fwrap v flag, which means that yes, int max plus 1 is int min, if you tell your compiler so. And then there's some things you just can't do in a compiler, because compilers need to be fast. I mean, they're gentle users. You don't want them to compile out twice as long because you're checking for all the possible warnings and whatnot. And you can do some further analysis in theory if you just look at what you can do with compiler engineering. And there's static analysis for that, where you really deeply analyze C code. And noticeably, there's the Clang static analyzer, which basically is derived from the Clang source code and gives you a lot of very interesting graphs. Actually, it can tell you, okay, if you take this 4 branches in if statements, right? So this is false, this is true, this is false, this is true. Then you might end up with a situation where that variable is in fact too large. So it's a shift amount of 32 or something like that. The NSS does that very well and shows you, so you might want to use that on location in the source code. And then if you see that even that can't spot, You have dynamic analyzers, which basically create instructions at runtime in your program and check certain conditions. So well-known is Valgrind, mostly as a memory checker, but you also can check for different things, also undefined behavior partially. And that's something else to try if you do lots of it. Okay, so today we're going to start with a question here. This is somewhat more contrived, but anyway. So the question again is, what does this simply print? This time we're again optimized, and we're using plain or GCC, it doesn't really matter. So we have a function, and our function takes 2 pointers. And we assign both pointers different values, as such fine, that we print the value of, well, the value at the location I points to. And we have our main function, and that creates an integer and calls this function, specifying the same variable twice, or the address of the same variable. So what would you think? I mean, obviously f is now pointing to the same memory I is pointing to, so it writes routine to the same memory, maybe, maybe not. So yeah, you think this prints 42. 3, 4 people. You think this prints 13. 1 person. Who thinks this prints 0? Also 1 person, I think. And who thinks this prints large randomish looking number? Okay, that's a lot. So this obviously prints 42. And the reason is quite simple, because this falls into the strict async, which basically just says, okay, if you have a memory that is of type integer, you cannot access it via anything else that's not of type integer. So what this does in fact is, okay, I have an access to a variable I, which means everything that wrote this variable must have had type integer. And there's just one thing that might have wrote this variable that has type integer and that set it 42. So it can be constant propagation. I can just put this 42 immediately here and print that, because f cannot possibly have changed it, right? This code will generate a 1 piece, FYI. So yeah, long version of that, C allows for aliasing. So if you set a pointer to an address of something, you have suddenly an alias. So the dereference of PA, the pointer in this case, alias is A, it's just the same object. I should probably say object is in terms of what C99 thinks, so this doesn't mean like C++ object or anything, but it's just representation of a variable in memory, it's an object. So since C99, not all expressions may be used to access an object. So this is actually new in C99, and that's not having fun with C99 possible. You really need to pay attention. You cannot just randomly cast things to float pointers and access them and expect that it will just all work. So the expression that you use to access this object in memory must have a matching type. And this is what's called the strict aliasing group. It's actually not called that in the standard, interestingly. The standard just has a note sort of next to this rule which says this is meant to restrict aliasing, but all the compilers and pretty much everyone else reference is the strict aliasing group. And so, yeah, as I've said, with some syndicates, the float pointer, you may not access an integer. So there are some exceptions. You can address that object with a different assignments. So if you have an unsigned integer, you may write to it with a signed integer pointer. You can have different qualifiers. So maybe volatile, not volatile. It may be a member of a, well, structured type. So it's a struct array of a union, which makes sense. So if you have an integer member of a struct, you obviously can change an integer if you change its struct. And then you may use character types. And that's actually, well, let's say it's nice of them, because in the standard community just noticed, okay, a lot of people do byte arithmetic on these things, and they'll access it on a byte granularity, so it's characters. So let's allow that, because it's actually useful. So, as I said, the reason for doing this is that it gives you a lot of potential for constant propagation, which is actually a quite valid optimization, one of the Dragon book optimizations if you're listening to compiler engineering. And what it basically means is if you assign something to an object and you don't have another assignment to the same object, you can just put the constant if you refer to that object again. So in this case, it basically means, okay, you assign to the 5 as you assign to I the value 5, so you can just call G with the parameter 5 instead of G referencing I and then taking that value, calling G with that. And if you didn't have the strict aliasing, this would be different. If you don't have strict aliasing, that's what it also says in the language, I think. You have to consider all data as invalid that you collected once you have a address-based write access. So basically, if you write to float, if you write to struct, if you write to anything based on a pointer, after you've assigned something, you have to invalidate all your constants. So you cannot reuse a constant past that point. And what strict aliasing allows you is basically to just have a lot more potential for constant propagation and actually help the code. Yes?
Is that true for the source type being void star 2, void pointer?
That's a good question. It doesn't say anything. Well, so basically what the standard says is you may not do this. And in the end, I showed the exceptions, void pointer is not one of them. I'm not sure what compilers actually do about this. The thing is, you cannot usually write to a void pointer anyway, because how do you assign to a void pointer? What do you cast to before that? The only thing you can do is cast to a void pointer and cast back to something. And once you've done that, you're certainly not following the strict aliasing rule, because in the end, you have an integer, you cast it to void pointer, you cast it to float pointer, and in the end, you're accessing an integer through a float. And that's not following the rule, obviously. So, yes, that sort of applies. Okay, so yeah, if you wanted to have aliases and you can control that sort of thing, you can put the two alias things in a union. So basically, if you have a float and a union, a float and an integer in the same union, you can assign to the float and just the compiler will know the integer may change and vice versa. This is helpful. Sometimes you cannot control that, which is annoying. There are actually some C APIs out there who make you do strange things. And the real solution to that, if you cannot control how the memory is allocated, is the function does that for you, something you actually need to use macro, which may or may not be efficient. Yes?
The last example, the first one, would be using software.
Pardon?
How would the union help here?
Yes, it would. So, yes, that's actually the point. So some people try to avoid this by putting 2 pointers in a union, which is not following the rule either. You actually need to allocate the objects in that way. So this is one of the cases where, yes, it is not possible. You can allocate a new float and then man copy from that float to I, but otherwise that's just not possible. What you can do, what is actually helpful in this case, and will get you probably a lot of more compiler warnings too, you can say that these 2 pointers are what's called restricted. So you can explicitly say these two may not have overlapping memory at all, which is completely different from your question, but still helpful in this case. So nobody would ever pass the same variable twice for both segments. Okay. So arrays. Well, let's see if I'm going to point them. So we have a declaration that this is the case where I expected to get the answer right. And we have a variable a, and it's equal to say array of characters with length 2. to pointer to character. Okay, lots. So that's what I was hoping for. So no, this rule I talked about does actually not apply recursively. You just do that once. So you have an object of type, well, the object is of type, array of character, and you apply the rule once. So basically the first array of in that type expression so is changed to pointer to. But you don't do that twice. So you get a pointer to array of character in the end. So yeah, I like that one too. So how do you declare a pointer to an array of integers? And I've tried to ask that people in preparation for this talk, and I think they got 0 correct answers. So who thinks it's well, the first one? Okay, who thinks it's the second option? Three brave persons. Who thinks it's the third option? What are you? And who thinks it's the fourth option? Okay, 1, 2, 2. Well, that's actually the first. And there's a rule of thumb here actually, which is declare it how you use it. So if you have a pointer to an array, what you first do is obviously, because it's a pointer to an array, you first dereference it, and then you use the array. So this is how it's declared, right? You use braces to make clear that the dereference is the first thing, and then you have the array indices. I mean, I'm not sure I should talk about the other ones. The second one is hopefully obvious. That's an array of pointers. Right, if you think about it, that's how you declare it. The third thing is actually an incomplete type, and as such, not a valid declaration. You can, however, use it in function prototypes. And in function prototypes, it's actually the same thing. Because in function prototypes, the first level of array of sort of is automatically converted to pointers. So you could actually put a size in the first brackets or not. It will always be pointed to an array if you use it in the function prototype. And well, the third one is just invalid code as a default. So yeah, as I said, generally well understood. And as I actually hopefully managed to demonstrate, there is sometimes confusion of the arrays into pointers. And this is in full quotes the rule I was talking about. So whenever you have expression that has a type array of type, or a type maybe anything, it is converted to an expression with type pointer to type. And you all got that basically right on the first question, but the thing is this does not apply recursively. So there are two exceptions to this, which are sort of obvious. This does not apply if you give it as a parameter to size of, which makes sense because if that applied, if you give it as a parameter to size of, if you use the size of some array, you would always just get your size of the pointer, which is not what you wanted, right? Which is a good catch, because if you do this in a function, and you had a parameter, and you declare that with those brackets, as I said, this will automatically be converted to a pointer, and you will get inside that function always the size of the pointer, which you might not have expected. And obviously, if you try to get the address of the array, this does also not apply. So this is, well, putting salt into the wound. So you often use it. It's basically a car pointer. You know, it's a two-dimensional array. And if you write this code, which assigns a two-dimensional array to a car pointer, you get a warning from the compiler, and it's a different type. I mean, the first one is pointed to array of car, well, the right element of the assignment. And the left one is pointed to car, so that's not the same thing. And as I've said, if you actually want to declare that pointed to array of car, because this assignment is valid, this is how the declaration is. So, and if I just cast this, somehow people get interesting ideas. So what if I put a cast around this and assign it that way, and the compiler won't give me a warning anymore? That will work, right? No, it will not, because that's what that exact memory is to me. It's absolutely clear. If you have a two-dimensional array, everything is just in memory one after the other. That's a large chunk. If you have a pointer to array, you actually have a set of pointers, so it's the right variant, and those pointers point to chunks. And they don't actually have to be right next to each other in memory either. So let's see if you understood this sort of. So we still have a two-dimensional pointer declared. So an array with a size of 3, of arrays with a size of 5. And we have this expression, which is basically put the array name, which is converted to pointer to array of car, and add 1, and the pointer is not available. So if we, well, let's say we put braces around it, you reference it to science. How many characters, like how many bytes after the start of the array B will we actually assign? We think it's 1 byte. Okay, we think it's 5 byte. Plenty. We think it's 10 byte. And who thinks it's 0 byte? Okay, so as most of you said, 5 byte. And the reason is quite simple, in fact. So as I said, this is a pointer to an array of car. The long version of that is it's a pointer to an array of size 5 of characters, and each character has the size of 1 byte. So basically, what you shifted by is the size of the second level array. So we shifted by array. So which is 5 bytes long. Okay. Let's talk about conversions, and let's talk about it quickly. So this is, as I said, about conversions which apply if you perform certain operations. And in this case, we have 2 declarations, one unsigned and one signed integer, with the values 1 and -1, and we just compare them. So who would say this prints true? Okay, who would say this prints nothing? Who would say this prints false? Who has no opinion at all? Well, and who would say this prints a mixture? Well, no. So everybody's still pondering. I'll give you the answer because we're running out of time. It's false. In this case, because we're in fact doing conversions, and I'll talk about the specific rules this conversion works on later, which basically says that the signed integer is converted to an unsigned integer, which means this is currently uint max, so a very huge number, basically, which is obviously which is larger than u. So s is larger than u, and we get false. Okay, so here we have addition. This time it's not 1 and -1, but 1 and -2, and we're printing the results. So who would say this prints -1? Okay, one person. Who thinks this prints 0? Who thinks this prints, I believe this is uint max plus 1 or something? Okay, few. And who thinks this prints 1? 1, 2, 3. Okay, so this is in fact -1, which is sort of what you expected, right? -2 plus 1 is -1. Totally, some of the results what you expected. And this is because the conversions are actually not random. They're chosen in a way that you often get exactly the result that you would expect. And specifically for addition, you pretty much always get the result that you expect. And the reason is basically the way that signed integers are converted to unsigned integers, which is by adding, what is it? I think the maximum number representable by an integer, and then that plus 1 to the signed integer until it fits into your type. And what that does is basically, if you know that sort of math, you're in a modular ring where everything is considered modulo uint max plus 1. And if you go from that ring back to signed numbers, assuming the result is positive, the result is actually well-defined, which means that this example is completely wrong. It is, yes. It's just that being should have been 2 and -1, I think. And then the result should be 1. Yes, I should explain that because if I ramble on, So what you get effective metering. Okay, so far so good. So you have your two unsigned numbers, but the congruent to say to some signed number which might be negative. But if you convert from an unsigned integer to a signed integer, and your unsigned integer is actually larger than what your signed integer can represent, we are in the zone of undefined behavior again. It just doesn't work. Or it might actually be implementation defined, but it's not portable as such. If, however, your result fits, so it is, for example, 1, the conversion is well defined. You can certainly cast a unsigned 1 to signed 1 and everything works. So if you're doing this arithmetic and your result is positive, which is where this example is from, casting effect is perfectly fine to get the result you expect. This case actually does work. It is, however, in that case, the implementation defined behavior where you have a very large unsigned number and your implementation somehow converts it back to a signed integer, and most compilers do this correctly in the way that you get -1 in this case. Okay, so how do these conversions work? There's a lot of theory behind this actually in the C standard if you look at it. And the first thing is integer conversion ranks, which are basically, it's a, well, rank, let's say it's a number, assigned to each integer type, and it's used to determine which integer type you need to convert to. And there's no fixed mapping. This is, so the mapping is completely implementation defined. However, there are rules by which to do this mapping. And the rough rule, and there's a whole set of them, but you don't really need to remember them. But just remember a larger range of values which can be stored in the variable equals a higher rank. And that's pretty much always the case. I've not found anything where the rule would break that. Also note, larger range means if you have something negative to something positive, that's the range. You don't go from 0 to highest positive value. So an unsigned integer and a signed integer do have the same range in terms of how big it is. It can represent the same amount of numbers. They're just at an offset. So they get the same conversion mechanism. So then there are integer conversions. And those are applied only if the type of the expression is of a lower rank than an unsigned integer, so character or short usually. And they're all converted to an int if your expression is representable by an integer. Otherwise, you convert it to an unsigned integer. And since the rank was lower, so the amount of values representable was smaller, this will always work. So when does it happen? That happens as part of the usual arithmetic conversions, and we'll see those later. Also default argument promotions. And then whenever you use the unary plus, minus, or not operators, where unary means if you just want -1, not as a subtraction, but just unary in front of what we have. And there's also plus like that, and bitwise negation actually in there. And then to both operands of the shift operators for whatever reason. So you basically, if you have that shift 1 to the right by 32, both the 1 as well as the 32 are first cast up to an integer, which can give you unexpected results if you were performing arithmetics on the character, because suddenly you would have expected that, well, you might have expected you got undefined behavior because you shifted the character by 9, and suddenly it was an integer. So 9 was well in the range of an integer because that's usually 16 or 32-bit. 16 if you were macros. So default arguments conversions. Say we have a function, and say we don't know the types of the parameters. So you don't have a prototype, which you can do in C. Nobody does that luckily, but you can do that. Also, if you have variadic functions, so something like printf, where you just can put any number of parameters at the end, you don't have a type for these parameters. And you need some rule what type to convert them to. And first you do the integer promotions, which we have just seen. So everything smaller than an integer is basically cast up to an integer. And all floats are converted to doubles, which you may or may not have noticed that %f and printf is actually the format specifier for double. additional operation, but in that case just to second and third argument. So what do? They do a lot of stuff. And I'm not going to go over this in detail, but I'm going to encourage you to look it up. So basically, if one thing is not double, the other thing, so you have two outputs, two classes, right? So if one of them is non-double, the other one also gets cast to non-double. If one is double, the other one also gets cast to double. If one is float, the other one also gets cast to float. So you go through the set of rules. And there are final ones. So at that point, if you're not finished, you do integer promotions, and then you look whether they have the same signs or not. As I said, I'm running out of time, so I'm not going to over this into detail. It's lengthy and complicated rules, but I encourage you to look them up, especially if you're not sure about what the expression actually does, and you're adding sort of lots of integer types with different sizes. So this is basically the example I've previously had as a question. So A and B have the same rank. As I said, unsigned and signed integer can represent the same amount of values, not the same values, but the same amount. And since they have the same rank, in this case, they fall through all of those rules we have just seen, and are both converted to non-signed integer. For both of these operations, the rules are exactly the same. And as we've seen, this means A, if A is larger than B, is false, but plus works just nicely. And in this case, it's a 0, so as I said, positive values and or 0 will work fine. So, final C99. So first thing I wanted to show you compound tools. Who has actually heard of compound tools before? Nobody, at least not another name. So they look like casting an initializer. And if you show that to something and say, have you seen that? They'll always say, of course. I use that all the time. And then you tell them what it is, and they say, whoa, what's that? I've never seen that. So in the end, it's really an anonymous object in C. And what it does in this case is you have an object, which is of type array3 of integer, and it's initialized with its values. And you don't need to do the assignment. This is not a way of initializing this. Well, it's not even right to initialize this pointer. It's a way of creating an anonymous object of type array of int. And what happens then is this anonymous object, because its type is array of int, the expression is converted to pointer to integer, and you can assign it to the pointer to integer. And you never actually created sort of an array. You just had this anonymous object and assigned it to a pointer. And I have no idea why. For some reason they decided, okay, we could make this a null value so that you can assign data to anonymous objects and never get back to it. For no apparent reason. But I think they're kind of cool. You can basically, I mean, the main usage for them is get around declaring a value, which is basically just, I want to get memory, and then we'll always just use it as a pointer. You can instead create an anonymous object, assign it to a pointer, and you have it with only declaring one instead of two variables, which is sort of neat. And then there are booleans in C99. Actually, new C have booleans. Okay, no things in it. So there's a real boolean type. It has the somewhat fancy name underlying bool, which is in uppercase B2. Luckily, there is a header for that, and that's also standard. It's called std bool.h. And what it basically does, it gives you a type of, which is then called bool. So you can declare a boolean as bool, just like in C++, and they just say this is for C++ compatibility, and gives you the usual constants true and false, which you also normally would have in C. Okay, so I think I'm pretty much out of time, so thank you for your attention. It's been a great audience. And I would take questions until somebody completely stops me. So for 1 or 2 minutes, I guess. If there are any. Yes? That's a very good question. I probably have to reread the rules. They allow for lots of stuff. They also allow for, and nobody uses this ever, they allow for sign magnitude. So that's valid. You can represent integers as whatever you want to. And you're probably right that yes, that would have one value less in that case if you use one's complement. I mean, sure, you're probably right in that things, they might still end up with the same rank, they might actually end up with different ranks, but let's get away with it. This doesn't happen in practice, because pretty much everyone uses two's complement because your hardware does that. So, yeah. But it's a good question. Feel free to read up on that.